All right, guys. So welcome back to another Math 230, 231 GSG session. So for today's GSG session, we'll be covering section 16.1 and 16.2. And yeah, and just as we did last week, I'll be looking at some examples from the textbook. All right, so let's get started. The whiteboard. Okay, so 16.1. So 16.1 was an introduction to vector fields. So I'm just going to go straight into the problems. So for 16.1, we'll start off with number 6. So number 6. All right, so let's see what we have. So for number 6, they give us a vector field f. So for this question, we're given fx comma y, which is equal to y I hat all over or minus x j hat over square root x squared plus y squared. And we're supposed to draw a diagram like figure 5 or 9. Okay. So yeah, they're expecting us to draw something like a vector field or slope field kind of diagram. Okay. So yeah, figure 5. Okay. All right, so let's see where we can start with this question. So first of all, what I would do is I'll split up my I and j components of this vector field. So I'll represent it as y over square root of x squared plus y squared, I hat, minus x over square root of x squared plus y squared, j hat. All right, so if I have to draw my axes, it's gonna look, so if I draw out my graph, say this is I, so x and y, we can see that at 1, 0, I'm just gonna label my 1% and, or 0, 1, sorry, 0, 1, and 0, -1. Right, if you notice that for f of 0, 1, we get that we have a unit vector in the opposite direction of I, right? Since x is going to be 0, this j term is going to be 0j, while for the I term, it's going to be something like 1 over the square root of 1, which is just 1 I. So that's actually going to be a unit vector pointing in the positive I direction. So for 0, 1, we're going to have something like this. And for 0, -1, we're going to have something like that. Right? Since in this case, we have a -1 for the value of y. And so for f of 0, -1, we have the same thing as -1 I hat. So it's going in the negative x direction. Yeah, the magnitude of 1. All right, so this is 0, 1. Right. And yeah, for these kind of questions, I'll start off by doing values of in the y-axis and x-axis. So I'm just going to pick up points of 1, 0 and -1, 0 for the x-axis. Right. So 1, 0. So I'm going to get, based off the vector field they give us. So for 1, 0, I get that y is 0, so it'll be 0 I hat minus 1 over 1 j hat. So we're going to have a curve look something like that. Well, at this point, it's going to look something like that. Right. So if we actually draw out all the different points, it's going to look something. You're going to have all the vectors of fx, y, unit vectors that are tangent to the circle centered at 0 at the origin. So you're going to have something looking like this. All right. So yeah, that should be it for number 6. You have this representation of this vector field right here. Okay, so that's number 6. All right, let's move on to the next one. So I have number 11 prepared for next question. Okay. So yeah, number 11 actually requires a image from the textbook. So let me just share that right now. So we can pull it up real quick. Number 11. Ah, right here. Okay, perfect. So you can annotate on this. Okay. There you go. All right, so number 11. We have the vector field F, and we're trying to match it with the plots labeled I to IV. All right, so for these kind of questions, what I usually do is I looked at all the different quadrants, first of all. So for this question right here, we notice that for the first quadrant, right? For the first quadrant, we have positive values of X and positive values of Y. So based off this, we're going to have something going in the, or rather, if it's a positive X value and a positive Y value, you're going to have the gradient going in the positive X direction, while the Y value going in the negative area. So we can eliminate option 1, right? Since the first quadrant is all shooting upwards. For number 11, we can say that it's not going to be I. It's not going to be II, right? Since this shoots upwards, right? We're trying to find when X is approaching a more positive number, it's going to go slope downwards. So it might be 3 or 4. Okay, just based off the elimination of the first quadrant. Now, if we plug in values in the second quadrant, which is negative X values and positive Y values, we're going to get that in the negative X direction, you're going to have these vectors sloping downwards. So based off the first 2 quadrants, we can actually deduce that fx comma y, where we have x comma negative y, that's actually going to represent IV for question number 11. Okay, so for number 11, I write this down. That would be graph IV. Okay. All right. So let's go over the next 3 to get a better understanding. All right. Just to reiterate, what I usually do for these kind of questions is just start off by looking at the different quadrants. Okay. And usually that will let you know which vector field is going to match to the plot. Okay. All right. So let's look at the next one for number 12. So we have y comma x minus y. All right, so for the first quadrant, we have positive x values and positive y values, right, for the first quadrant. So for the first quadrant, we want that since x follows y, it's for the x side of things, as you're looking at the first quadrant, that's going to go and increase. While in the y side of things, it's going to have x minus y, right? So that's actually going to look something like this right here. Graph number 3, yes. And the reason why that is because, let's look at this real quick. X minus y, right? Yes, that should be it. Yep, okay. All right, so for the y, for the x value, since we're looking at this vector field right here, right? Since my y values are always going to be positive, we're always going to point to the right direction. So based off that, we can eliminate option 2, right? Since option 2, part of the vector field is actually sways to the left. Like as you can see, this vector sways to the left, right? These vectors stay to the left. So we're basically condensed down to option 1 and option 3. Right, so that's based off quadrant 1. Now for quadrant 2, right? For quadrant 2, we still have positive y values. So you should look at the graph going into the right direction. So still, these 2 are valid. Now let's look at the y component of this vector field equation. So we have x minus y, right? So whenever the x values are greater than the y value, we have a positive slope. While whenever we have a y value greater than a x value, we have that it's going to be negative. So as we can see right here, right, as x approaches a negative value, right, and y is always positive in the second quadrant, this is always going to result into a negative value for y. And that's why all these vectors are pointing downwards. Okay, and that's why for number 12, this should connect to plot number 3, right? Because as you can see in plot number 1, for the second quadrant, we can see that it's all pointing upwards, right? But since based off the equation that x minus, for the y part of this vector field, that we have x minus y, right? Since we have a negative x value and a positive y value, x minus y is going to result into it pointing downwards instead of upwards. And that's why for number 12, we have that the plot matches plot number 3. All right, so now let's look at number 13. So y and y plus 2. All right, so what we can see from this is that whenever you're dealing with positive values of y, it's always going to go to the right. So first and second quadrant should have vectors going to the right and up, right? So based off just these two equations, we can deduce that it's not going to be plot number 2, just because in the first quadrant, we have positive x values and positive y values, right? And since the x part of the vector field actually depends on y, x will always shoot to the right. And since, y is positive, it'll just shoot upwards, okay? And same thing goes with the y plus 2. Y plus 2, that's the y part of the vectors, so that's always going to shoot upwards if y is a positive value. So that's first and second quadrant. Now let's look why this behavior actually is the case. So like I'm assuming right here, we notice that some vectors actually slope upwards while some vectors actually slope downwards, right? The reason why that is because this is roughly where y is equal to -2. Right? Because what we notice is that whenever y is a negative number, we have this vector field pointing to the left, right? Since in the x, right, whenever y is negative, you're going more to the left, right? And that's why as you go downwards, you're going more to the left, while if you're going upwards to the y-axis, you're going more towards the right. But looking at y plus 2, we notice that whenever y is greater than -2, we have y plus 2 being greater than 0. All right, so that's why from this line and everything underneath this line will have vectors pointing slightly downwards, and the farther it is, the more it points downwards. And that explains the vector field, or y plus 2 part of this vector field. Okay, so that the 13 is actually going to represent plot I. All right, and then lastly, cosine x plus y. All right, I'm just going to start off by looking at this x part of the vector field. So as x is a positive value, you're going to have that y goes upwards. So we can see that if I just split this graph, this plot into 2, just right across the y-axis, you can see that whenever x is positive, we have that y is sloping upwards. And if you look at all the vector fields, they are all sloping slightly upwards, okay? And same thing goes with whenever x is negative. We have all the vectors going downwards, okay? So that explains the x part. And for cosine x plus y, right, that actually depends on, and that's why for 0, right, 0, 0, cosine of 0, we have 1. And that's why it should just twirl around, and I'm assuming this right here is going to represent roughly pi over 2 radians. Okay, and same thing goes with whatever is in here. Right, and so this again is just going to represent II. All right, so yeah, that actually solves all the questions for matching vector fields with the plots. All right, so that was number 11 to 14. Now let's move on to 15 and 17. All right, 15 and 17 are kind of similar to these questions we've covered, but they're in R3. Let's see if I can share that photo. Okay, so 15. So start off with, I'm just going to cover 15 and 17 for this section. So for 15, what we notice is that all the vectors actually point in the same direction, right? We have, for the x coordinates, we have that, I has a constant coefficient of 1, j has a constant coefficient of 2, while k has a constant coefficient of 3. So what we can say is they're all positive, right? They're all going in the positive direction. And then, so for x values, they're always going in the positive x direction, right? And we have x1, y of 2, and then z of 3. Yeah, that should deduce down to IV for this question right here. And the reason why that is because as you can see from, I think, this is just a rough sketch. What you notice is that the z values is always going to be a 3. So that's why it's always going to point upwards, right? So for the z values, it's going to go upwards. Now for the y values, you're going in the direction of the positive y of 2. So that's why you're going this way, right? No matter what y value you're at, right? You're going this way. So if I erase this, right? You're going you're going this way at a magnitude of 2. And lastly, for the x, you're going in the positive x direction. Okay. All right. And that's why 15 should be plot IV. Okay. And then for number 17, for number 17, we have that the I coordinate is dependent on x and the j coordinate is dependent on y. So that might change things up for this question. For number 17, we have, x, so in the I direction, or rather in the k direction. So we know based off this that in the z direction, it's always going to point upwards. So actually, just based off this term right here, we can deduce that it's this plot. So this is actually going to be plot III, right? And the reason why is because plot number 1 goes downwards when z is less than 0. And plot 2, it does also go in the negative direction when z is less than 0. Okay, so so let me just stick to number 17. So for number 17, as we said, z is always positive, so it's always going to go upwards. Now let's look at the jth component. So the jth component actually depends on y, right? So the more towards 0 you are, the more in line you are with 0, and that's why as you get closer to 0, you notice that the vectors actually go more vertical, right? While if you go in the more negative y direction, right, these vectors actually point towards, or points more in the negative direction, as you can see. And while you go in the positive direction, it goes more towards the right, or the positive y direction, right? Same thing goes with the ith component of this vector field, right? You start with 0, more vertical, and then more positive to the left, right? As you go more positive, vectors go more towards the left, and as x goes more negative, it goes more to the right. Okay. One thing to watch out is just watch where the numbers are going, because in this case, right, -1 is towards the right, and positive is towards the left. Okay, and that's why 17 is going to match up plot 3. Actually, let's finish off this section. So let's do number 16 and 18 too with this one. So for 16, we can see that the ith component and the j component is always going to be positive. So we can say that the y direction is always going to go towards the right, or the jth component, sorry. The jth component is always going to the right, while the x component is always going to the left. Yep, since left is positive. Okay. And yeah, that's just based off these two terms, I plus 2j. Okay. But since k is dependent on z, we can see, and I think I briefly mentioned it before, that anything above z equals 0 will have vectors pointing upwards, as you can see. And anything below z equals 0, we have that the vectors point downwards. Okay. And that's why 16 should match up to plot I. Then last but not least, we have xi plus yj plus zk. And this will just start off in the origin and just goes basically it will just go based on the z values, y values, and x values. So the more towards 0 you are, the more you are going in the y direction, or like, yeah, more this way. Okay, so like let's look at this point right here, right? Since you're going more towards the positive x, right? So the ith component will go more towards the left of this axis right here. While if you go to the negative x direction, it'll go more towards the right. The vectors will go more towards the right based off this x-axis. Same thing goes with y. Think of y going like as a, so if I was this kind of being my separator, all right, more towards the left, you're going this way, while y with a positive value going more towards the right of the y-axis and left for negative values of y. And then lastly, we have the z cutting across. And so if we see that, everything above z is greater than 0, we have the vectors going upwards, and anything below 0, we have z going downwards. And that's why 18 is going to match with I. Okay, plot number 2. All right, so that's it for 15 to 18. And then let's cover 29 and 31. So yeah, 29 and 31 are actually 2 more graph questions. All right. And then, yeah, after this, we should move on to 16.2. All right, so let's see what we have. So 29 is fx comma y is equal to x squared plus y squared. And then we're going to plot of their gradient vectors. Okay, so for these kind of questions, you first have to find the gradient vector. So for 29, oh, sorry. Let me start off by finding the gradient vector. So for 29, the gradient vector f is going to be in the form of be 2x for the x component and 2y for the y component. Okay. So based off that, we can see, let's check the maps, the plots. So for the first quadrant, again, since the x and the y values are positive, it's always going to go in the positive x and y direction. So we can eliminate option number 1, right? We can eliminate option number 1, and we can eliminate, yeah, I think that's it. Yeah, just option number 1, just based off the first quadrant. Now let's look at the second quadrant. So for the second quadrant, we have 2x comma 2y. So if we have negative x values and negative y values, my curve or my vectors for the second quadrant is actually going to look something like this. Oh wait, sorry, negative x values and positive y values. So it's going to look something like this for the second quadrant. So we can eliminate option number 2 based off that. And actually option number 4. So we're left with option number 3. So for 29, it's actually just going to be option number 3. And we can just verify the third quadrant. It's going to go in the negative x direction and negative y direction. So it's going to, vectors are going to go this way, right? And lastly, for the fourth quadrant, since your x values are positive, y values are negative, we have the vectors going in the positive x direction, but also in the negative y. So we'll have vectors going this way. Okay. All right, so that's number 29, and let's look over 31. So x plus y squared. Okay, so where's all this? How can I annotate? Actually, I can annotate this way. All right, so let's see. So for 31, we have that fx comma y is equal to x plus y squared. So finding the gradient of fx comma y is going to give me, so for the x component, it's going to be 2x plus y, right? Well, the y component is going to be actually the same exact thing. All right, so let's look at that. All right, so they're actually going to behave the same way for x and y. All right, so for positive x and y values, so for the first quadrant, we have positive x and positive y values. And since they don't have a negative, right, x component is just going to go to the right, and then y component is going to go upwards. So we're going to have something like this. All right, so again, we can eliminate option number 1. We have to leave option number 2, 3, and 4 open. Okay, so let's look at quadrant number 2 next. So number 2 is, yes, it might have a condition. Okay, so we'll cover this. So for the x values is always going to be negative, right? Negative x, and y values are always going to be positive y. Now let's look at just 2x plus y. You notice that if negative x is greater than y, then it's going to go in the negative x direction, and y is also going to go in the negative direction. So it's going to go this, yeah. So based off this, if negative x is greater than y, we have the vector pointing in this way. However, if negative x is less than y, my values for the x component of the vector field and the y component are going to be positive. So we have that the vector is going to point upwards. And that's why just by looking at the graphs, we can see that for graph number 2, right here, right, what we notice is that whenever the negative x has the same magnitude as a y value, so let's say this is what, negative 3, and let's say this is positive 3, the vector field actually doesn't go anywhere. And you see that's represented by a dot. And anything below that for the second and the fourth quadrant is going to go downwards, while anything above that is going to go upwards. And this is the same exact thing for the fourth quadrant. Okay. All right, and now for the third quadrant, since it's always in the negative direction, you're always going to have a vector going this way. All right, so that's number 31. 31 should match up to plot number 2. All right, okay, so I think that wraps it up for chapter 16.1. Let's move on to 16.2 now. 16.2 is less of plots and more of solving line integrals. Okay, so let me just pull up our whiteboard for that. Okay. All right, so 16.2. Now for 16.2, what I would say is this formula is going to be really handy. So, yeah. We're going to be using a lot of the line integral formula. Okay, and we'll see that right as we start the questions. So I have number 3 prepared for now. Okay. Number 3. All right, so it says evaluate the line integral where c is the given curve. So number 3, we're given the integral of c of xy to the power of 4 of ds, where c represents the right half of the circle. Circle x squared plus y squared is equal to 16. 16. Now, one thing to remember is that the d of s is actually going to represent the square root of dx over dt squared plus dy over dt squared times dt in this question. The reason why that is because, it's basically because we're going to represent x in terms of a cosine function in terms of time and y as a sine function in terms of time. So what we can say for this question is we can represent x as a 4 cosine t based off of the constraint that c is a circle with radius of 4. Right? We can represent x as 4 cosine t and y as 4 of sine t. Right? And that just comes from this constraint that I give us. Now, if we plug it back into the equation, we just get, So we have this, we have x, and d of s is going to be the same thing as the square root of dx over dt squared plus dy over dt squared. So if you can sub everything in, it's going to be the integral of 4 cosine t times 4 sine t to the power of 4. Multiplied by the square root of, so dx over dt is going to be 4 or negative 4 sine t squared plus 4 cosine t squared times dt. Okay. Now let's not forget about the bounds. So since we're only considering the right half of the circle, right? So if I were to write this down, right? Now, I'm going to represent t in radians form. So this circle, right, of radius 4, what I can say is that for the right half, it starts from negative pi over 2 up until when t is equal to pi over 2, right? Since we're only considering the right half of the circle. So I can say that my bounds are going to be from negative pi over 2 up until pi over 2. Okay, so these are going to be my bounds for this question. Now let's see. Yeah, we can definitely simplify this down. Now we have the integral of negative pi over 2 to pi over 2. Take the 4 to the power of 5 out. We have cosine of t, sine of power of 4t. To the square root of 16. Yes, because that squared distributes out to the sine squared, and then sine squared plus cosine squared is just 1. So we just have 16 times dt. And so this actually simplifies down to 4 to the power of 6 of the integral from negative pi over 2 up to pi over 2 cosine t times sine to the power of 4t dt. And then based off this is just a simple u sub. So if I did the integral, that will give me 4 to the power of 6. 4 to the power of 6, times cosine t, so that's 1/5 sine to the power of 5t, right? Since I'm going to set my u as sine of t, while du is equal to cosine of t times dt. Okay. So we then just integrate that. That's going to be bounded from negative pi over 2 up to pi over 2. And I'll just leave that computation as this. So this is going to be my answer. Yep, that's the one to go. All right, so that was number 3 from the textbook. Okay, so now let's look at number 7 from 16.2. All right, so number 7. Good. All right, so for number 7, they give us, again, another line integral question. But we have x plus 2y times dx plus x squared times dy. And then C consists of line segments from 0, 0 2, 2 comma 1, and 2 comma 1, 2, 3 comma 0. Okay, so I'm just going to start off by drawing out the line segments. So if I draw it out, we start at the origin, then we go up till 2 comma 1, and then we end off in 3 comma 0. So what I can do is I can actually represent this into 2 line segments. So I'm going to label that C1 and label that as C2. Okay. And so for this question, what I can do is I can rewrite everything in terms of x. So let's look at C1 first of all. So for C1, I can say that y is actually equal to 1/2 of x, right? Just based off 0, 0 up to 2, 1, right? Yeah. And so since y is equal to 1/2 of x, x just moves across just like an x, right? As x is 0, x is going to equal to 0, and if x is equal to 2, x is going to equal to 2. But if x is equal to 2, y is going to equal to 1, and that's why we have this equation right here. And so from this, I can deduce that dy over dx is the same thing as 1/2 dx. And from this, I can say that dy is equal to 1/2 dx. And that's going to be useful because we're going to see a bit of a substitution later on. Okay. All right. And that's for C1. Now for C2, oh, wait, one last thing I want to also mention is, yeah, this is definitely worth mentioning, is that C1 is bounded between 0 and 2 for my x values, right? Since we're just cutting it off right there, C1 actually goes, or its x value starts from 0 up only until 2. Okay. So for C2, we start off, and let me just start off with the bounds. So we're going to say that x is going to be bounded between the region of 2 and 3. And then for C2, we have that, again, I'm going to leave x as is. But we have that y is equal to x minus 3. 3 minus x, sorry. 3 minus x. Yep. And so based off this, dy over dx is equal to -1, and hence dy is equal to negative dx. Okay. All right, so now let's actually get to solving this line integral. Okay, so I need to set up 2 different integrals. One for my C1 and one for my C2. So for C1, we have, again, the equation was x plus 2y plus 2y dx or dy dx plus x squared of x squared times dy. And we add it to the second line segment as same exact equation. All right, and this is why I single out for dy. And the reason why is I'm going to sub it back in. So for C1, we're bounded between 0 up to 2 for my x values, right? So when x is equal to 0 and x is equal to 2. Now, x is going to stay the same. However, y is going to be the same thing as 1/2 x. So we have 2 times 1/2 x right there. Now, dx is going to stay the same while we add in, sorry, so let me just separate these 2 integrals. All right, so we have this added to x squared. So x stays the same, multiplied by, oh wait, I'm missing something.
Do you mind quick this to
Sorry.
The only reason is that this lab is so hot.
Oh, okay. Yeah, I'll be recording stuff, so yeah.
Well, it doesn't matter because it's only 10 minutes left.
All right, yeah.
In general, I think we're going to keep this to
All right, that's good.
just because it's cool in here.
Yeah.
All right.
Thanks.
Okay, so what we have here is dy is equal to negative dx. And then, yeah, where was I? Sorry for the interruption. So, yeah, okay. All right, so let's go back to this right here. So we have x squared. And then, yeah, x squared. So dy for C1 is actually going to be 1/2 dx. So I'm just going to multiply that by 1/2 dx. Right, so that's going to be the first integral setup. And now this is going to be added between 2 up to 3 of x plus 2 times y. And y is going to be 3 minus x. So that's going to be 2 times 3 minus x dx. And that's going to be added to x squared times negative dx. Okay. All right, so let's compute this out. So let's simplify this off first. So we have 0 to 2 of x plus 1/2 x squared of dx. And then we're adding to 2 to 3. And so we have x plus 6 minus 2x minus x squared. Yeah, x squared, and multiply that by dx. All right, so yeah, you can simplify this further, 0 to 2, and we'll get 2x plus 1/2 x squared times d of x plus, let's go from 2 to 3, multiplied by 6 minus x squared dx. Right, and I think I'll just leave it right there for you guys to compute. Okay, because yeah, this one's just basic integrals. Yeah, no u substitution or integral by parts. All right, so that was number 7. I have 15 minutes. So okay, number 15. All right, I think, yeah, this is the last question I have for this section of 16.2. So number 15. Okay, so number 15, we have the, again, line integral from z squared. So we have z squared dx plus x squared dy plus y squared dz. And now it gives us the, for number 15, it gives us C is this line segment from 1, 0, 0 to 4, 1, 2. All right, so I'll start off by just drawing out the plot and what this line segment looks like. So x, y, z. So we have x as 1, y is 0, and z is 0. So that's going to be that point right there. And it goes up till 4, 1, 2. So somewhere around here. So we have this line segment right there. All right, so what I want to do is I want to start off by writing down my parametric equations for this line segment. So what I can say is that for my x values, so let's say this is t equals to 0. Let's say this point is t equals 0, and let's say that point is t is equal to 1. I can say that for my x values, it's gonna be 1 plus 3t, right? Based on the fact that at t equals to 1, we have an x value of 4, and at t equals to 0, we have an x value of 1. So 4, 1, 2 is right there. All right, now my y is actually going to just be t, right? Because it just increments up by 1, and then it starts out as 0, so it'll be 0 plus t. And then my parametric equation for z is just gonna be 0 plus 2t. All right, so I have that set up. I can find my values. I can find my values for dx, dy, and dz. And so let's just set up the integral. So for my first part of the integral, it's going to be from 0 up to 1, right? 0 up to 1, where, right, because I'm just basically stating that t starts from 0 and up to t equals to 1. So t is equal to 1. Now we have z squared, so that's going to be 2t squared. Now dx is actually going to be the same thing as 3 dt. Now we add that, right? Because if you take that derivative in terms of time, we get that it is equal to 3, and hence dx is equal to 3 dt. So we have, yeah, 3 dt right there, and then we have x squared, so that's going to be 1 plus 3t squared times dy, so that's just going to be dy over dt is equal to 1. Hence dy is equal to dt. Then lastly, we have that y squared, so t squared multiplied by 2 dt. All right, so you can simplify that down. So we're solving this integral from 0 to 1 of 2 or 4 t squared times 3 plus 1 plus 6t plus 9t squared plus 2t squared, all in terms of dt. Okay, so I'll leave that right there. That's going to be the solution for number 15. All right, I have one more question prep for today's session, and we'll end off there. All right, so number 17. No, we just covered. So I have 17. All right, so number 20 from the textbook. All right, let's see what number 20 says. Okay, so we've got the line integral is given by the vector function RT. All right, so we're given that, we're given the function f in terms of x comma y comma z of x plus y squared in the ith component added to xz in the jth component plus y plus z in the k component. Now, they also specify that r of t is equal to t squared I hat plus t cubed j hat minus 2t k hat. And they specify that we're constraining time from 0 up till 2. Yes. Okay. So what you want to do for this question is, how I normally set this up is I'm going to use this line integral formula that we covered in lecture. So we have that we have this vector, f vector multiplied by the derivative of the r vector. And so what I need first is I need to rewrite the function that we're given in terms of time. So I'm just going to plug in r of t into f. And that's going to be the same thing as, so x is going to represent t squared. So we just want to plug in t squared plus y squared is going to be t cubed to the power of 2. That's going to be my ith component. Plus x is going to be t squared, while z is going to be negative 2t for my jth component of FRT plus t cubed minus 2t for my kth component. All right, and what I'm supposed to do with this is I'm supposed to take this and the derivative of r. So I'm supposed to do the dot product between the two different vectors and find a scalar product of those two. So let me take the derivative of r of t first. So r of t is going to yield 2t for the ith component, 3t squared for the jth component, and finally negative 2. So taking the dot product between the two, I get that, okay, we're bounding this from 0 to 2 for time. Now f dot r prime t is going to be 2t multiplied by, oh, all right, multiplied by t squared plus t to the power 6. And then this, since this is going to be a scalar product, I'm just going to add this onto 3t squared multiplied by t squared and negative 2t. So that's multiplying the j component of each vector. And then finally, for the kth component, it's just going to be negative 2 multiplied by t cubed minus 2t. All right, and this is all going to be derived in terms of dt. Right, I can simplify this down. And we will get, let's see what we get. So we get doing the integral from 0 to 2. And simplifying it down, I get 2t multiplied by t. So let me just write it down again. So 2t multiplied by t squared plus t to the power 6 plus, so we have 3t squared times t squared, so that's 3 to the t power 4 multiplied by negative 2t. And we're adding this with negative 2t cubed plus 4t. Integrating this in respect to time. All right, so simplifying this, I get 0 to 2 of 2t cubed plus 2t seventh minus 6t power 5 minus 2t cubed and added on to 4t. All right, so I'm just gonna leave this right there for you guys to solve. Yeah, because this one should just be a simple integral, and no u sub and no parts. All right, so yeah, that should wrap it up for today's session. If you guys have any questions, feel free to post them on Piazza, and I should get back with any questions you have either through Piazza or by next week's GSG session. All right, thanks for tuning in, and I'll see you next week.